Thank you very much. It's really a pleasure to see you. And so I'm going to talk about a use of greedy algorithms for training special form of neural networks. And I would like to start with this short description of what neural networks is, because I think that many people are familiar with neural networks but are not coming to this type of workshop. And I think there is an opportunity here for Optimizer to think about these problems as well. So let me start with describing what is a single neuron. A single neuron is simply a function that takes d-dimensional features, a d-dimensional vector, multiply it by a d-dimensional vector. So these are the weights. Okay, so we perform inner product between the input x and the weights v. And then we transform the output value, which is a real number. We transform it through an activation function, sigma. Sigma is simply a function from R to R. And usually, sigma is taken to be some sigmoidal function, like what is depicted here. And this is the output of the single neuron. Okay? So a neural network is simply stacking together many, many neurons, usually in a feed-forward manner. So we start with an input layer. These are our features. Then each neuron in the first layer receive them, multiply by some weights, and then pass it through the activation function. The outputs of the neurons in the first hidden layer goes to the second hidden layer, and so on until the output layer, which is, for simplicity, just a single neuron. Okay, so this is a model, a very simple model. Okay, so why should you care about deep neural networks beside Zuckerberg that came to the workshop? Okay, so usually the answer is because some guy A used it to do some task B. Okay, this is of course not a good explanation. So let's start about something more formal. So a classic explanation is that neural networks are universal approximators. What does this mean? It means that every Lipschitz function from d-dimensional space into, say, -1 to 1 can be approximated by a neural network. Okay, this is a nice property, so we can approximate every function. So we want our target function can also be approximated by a neural network. So let's learn it using the neural networks. But this explanation, although classical, is not convincing, because it is quite easy to show that in order for a network to express all functions over d variables, the size of the network must be exponentially large in the input dimension. Okay? And of course, you don't want to learn a network of exponential size. What would you do with such a network? Okay? Another reason why this explanation is not satisfactory, because there are many other ways to obtain a universal approximator. So if you do care about universal approximators, why not using SVM? Why prefer neural networks over SVM or some other nearest neighbor, boosting with decision stumps? All these are universal approximator, and all of these should be exponentially large in order to be universal approximator. So this is not a good explanation. Instead, I'm going to suggest you, yes?
Just to be clear, when you say exponential in D, that's when it's only one layer?
No, even multi-layer.
Even if you
need a deep network, still the size, the number of neurons in the network must be exponential. And if you want to understand why, it's a simple counting argument. So think about just Boolean functions. Okay? How many Boolean functions over d variables are there? 2 to the power of 2 to the power of d.
But
and the amount of
as well, right? So
yes, but I mean, even you can discretize the weight, and you can see that it won't help you. You must have many, many neurons in order for this to work. Okay?
But the argument of Yoshua Bengio that deep learning was needed because it was more efficient, it was still exponential. It was just less exponential than the other one.
Yes. No. I will come to this back in a minute. Okay. Deep networks are more expressive than shallow networks. That's true. But they cannot explain all of the functions. Okay, so I will come to this question in a minute. Okay. So I would like to suggest why I think that neural networks are great, and I would like to suggest something that comes from the basic of statistical learning theory. So what we do in statistical learning, our goal is to learn a function h from some domain x to some domain y. Think about x as rd and y as plus minus 1 or something like that. And the input to the learning algorithm is a training set of m examples. Each example is a pair of input-output. And from this input, we want to find a function h which is good. Now, there is a very well-known theorem in statistical learning theory, the no free lunch theorem. This theorem tells you that no algorithm can be good with respect to all distributions, with respect to all words. So more formally, for any algorithm A and any sample size M, there exists some distribution D over X and Y. So this is our word. And the target function H star that we want to learn, such that H star is perfect with respect to D, meaning that it has a zero loss with respect to D. But with high probability over a sample of M examples, the output of A would be very bad. Okay? So no algorithm can be consistent or perfect with respect to all words if you restrict the sample size to be fixed in advance. And the moral of this no free lunch theorem is that in order to learn efficiently, we must have some prior knowledge on the problem at hand, on the word that we would like to learn. So we must bias the learner toward reasonable functions. And one way to describe such bias is by assuming that the target, at least approximately, comes from hypothesis class H, which is a subset of functions from X to Y. Now the question is, how should you bias the learner? Okay, what should be the bias H? Okay, of course, if we know that H comes from some specific domain, then we can choose H to be, something that we know in advance that would be good. But in general, what should we do? So one very basic idea is to consider H, this class H, to be all the functions over D variables that can be executed in a certain amount of time. The rationale behind this is that we learn something and then we need to use it to solve some problem, right? So we don't care about predictors that takes a lot of time at test time. So in any case, we care only about something that can be executed efficiently. So let's decide what is efficiently, what is the amount of time that we allow the learner in test time, not the learner, the predictor in test time, and then describe the functions to be all of these functions. This is a very natural restriction because we basically do not lose anything, okay? Now, a basic theory in complexity is that the class of neural networks of depth order of t, d, and size square of this contains all the functions that can be executed in time at most td. So Simon, this is for your question. If you take deeper function, you obtain things that can be executed faster, okay? Or that can be executed actually longer. So you enrich your class. So you do enrich your class once you take deeper networks, okay?
How big are the constants hiding in the big O?
In the big O?
Yeah.
Does it really matter? I actually don't know. This is a basic result in complexity. I'm not sure what is a constant. Okay. So this is a great hypothesis class. Basically, with sufficiently large network depth and size, we can express all the functions that we care about. And also, we can understand the sample complexity, or how many examples we need to learn such networks. This is also well understood. For example, you can see in the book of Anthony and Bartlett. So is this the end of the story? Okay, we found the ultimate hypothesis class to learn. Of course not. Of course, the problem is a computational barrier, or how do we train neural networks. And from here, in practice, comes the thing that we do not understand at all. So my first message in this talk is that statistically, neural networks are excellent, are great. Okay? The main problem with neural networks is how do we train neural networks? And now, if there are optimizers in the crowd, this is your job, right? Okay? So the bad news is that it is NP hard to implement empirical risk minimization, which is our basic algorithm for learning hypothesis classes. Even if we only look at depth 2 networks, just single hidden layer with just 3 hidden neurons, and the activation function is sigmoidal or sine, and this is also a classic result by Blum and Rivest, and later on it was made stronger by Bartlett and Ben David. So the current approaches for training neural networks is to use some heuristics, usually backpropagation, which is some sort of gradient descent or stochastic gradient descent, possibly with some unsupervised pre-training and other bells and whistles that help it converges. But there are no theoretical guarantees, and often it requires a lot of manual tweaking. OK, so after this long introduction, I will come to the actual outline of the talk. And the main questions that I would like to touch is how to circumvent hardness. Ideas of can we come up with network architectures such that training can be made efficiently. So the first idea is called overspecification. And this is an idea I actually heard from Jan LeCun over dinner. And I will tell you about it, and we try to formalize it. It comes from, it begins with some empirical observation, and we try to make it more formal. I will show one positive result, but then the problem with this positive result. Then the second idea is that if something is difficult, let's make the network easier or a little bit different, and hopefully this change will enable us to come up with efficient algorithms. So what we are going to change is the activation function. So recall that usually the activation function are sigmoidal function. This is nonlinear function, which are quite complicated. A much simpler nonlinear function is just a square function. Okay, this is maybe the trivial, the simplest nonlinear function. Okay, so we will consider networks with just square as the activation function, and then I will show you an efficient learning algorithm for training such networks of depth 2, and the tool is forward greedy selection. Then the question is, what about networks of larger depth? And I will show some hardness result for very deep sum product networks. And there is a big open question of what comes in between. Okay? So let's start with the idea of overspecification. So Jan LeCun told me this story. You fix a network architecture, and then you generate data according to it. So you know that the data is generated from the model. Now you try backpropagation to learn the network from the data, and backpropagation fails. However, if you take a larger network and run it over the data that was generated by the smaller network, then suddenly backpropagation works just fine. Okay? So taking a larger network is something that Jan called overspecification of the network. So the question is, maybe overspecification helps you to eliminate the computational barrier. So the first positive result is, yes, it does help you if it is extreme overspecification. So what's the result? Let X be the data matrix. So we have M examples, and each example is in D dimension. Now we take a network where you have N internal neurons corresponding to hidden neurons. V are all the weights in the network except for the last layer. FV on X is the evaluations of internal neurons over the data matrix X. So FV over X is a matrix with N over M entries, okay? And W are the weights over all the hidden neurons, okay? So W is capital N dimensional vector, and then the output of the network is just the inner product between W and all the rest of the hidden neurons, okay? Now the theorem is that if we are overspecified to the level that the number of hidden neurons is greater or equal to the number of examples, then under mild conditions on F, just mild condition on the activation function that you actually use, the optimization problem of minimizing over both the weights W and V of the output of the network minus the target value square, this optimization problem has no local minima. Now, there are many, many, many minima. There is no single minima. It's not convex. It's highly non-convex. It looks like this. But all the local minima are also global ones, okay? And the idea of the proof is that with high probability over perturbations of the weights V, the matrix FVX has full rank. Now, once this matrix have full rank, you can optimize just over W and decrease the objective, meaning that if you are not in the global optimum, you have a way to continue go down. And since this is with high probability over perturbation of V, it means that it dents. So the points which are local minima are of zero mass, okay? So this looks great. But of course, the problem is that I wanted the network to be so large that the number of hidden neurons are actually larger than the number of examples. And such networks will probably overfit to the data and will not generalize. Yeah.
Does the nonlinearity that there is normally at the end change anything for your result?
No. You mean the loss function at the end, this one? Doesn't change anything. I mean, if you want to have nonlinearity here, I didn't have any nonlinearity on the output neuron. But if you want to have, as long as it's continuous function,
Yeah,
it's fine.
Using squared.
No, this result is actually not for square activation, for any reasonable activation function.
So if you had a sigmoid on WT,
That's fine. That's fine. Yes.
Are you saying there are no local minima, or that the set of local minima is zero measure?
It's of zero measure.
So anything can be exponentially negative.
It doesn't matter because, I mean, you will never go there in any reasonable algorithm. So if you do back propagation, you will not stuck there.
I mean, don't most smooth functions or whatever have their set of local minima being zero measure?
Yeah, that's a good point. That's a good point. I think that there is no local minima at all because the perturbation make the set of matrices of full rank dense. But in any case, the main message here is the following: take any reasonable algorithm, okay, such as backpropagation algorithm, gradient descent, anything that is being reasonable. Such an algorithm can go to the global minimum very, very easily. It will not stuck. So what you observe in practice in Jan's experiment will actually happen. Okay, and the reason it
Local minimum algorithm started close to it will be stuck there.
no, it will not be stuck there because just tiny perturbation will take you completely out of that.
I think all the local minima are when like V is symmetric. Then you effectively have less neurons and you can get stuck. But if you, that's why you have the overperturbation.
Yeah, but anyway, this result in any case is just a teaser, but it's not interesting because of the statistical thing. So let's not get into this, mathematical details, because in any case, it's not an interesting result, okay? So the question is, maybe there is a clever trick to overcome the statistical problem, okay? Maybe regularization, dropout, which is another kind of regularization, can make you overcome this statistical problem, okay? So the answer is no in the worst case, and the answer is based on a recent work with a student of mine, Amit Danieli, and with Nati Lineal, showing that even if the data is perfectly generated by a neural network of depth 2 with only k equals little omega of 1 neurons in the hidden layer, there is no algorithm that can achieve small test error. Now, what does it mean that there is no algorithm that can achieve small test error? It means that you can do whatever you want to learn it, as long as the algorithm is efficient. So you can do overspecification with dropout, with whatever bells and whistles that you want. Everything is allowed. The only requirement that you need to have is that you output a function that has a small test error. And this theorem tells you that there is no algorithm that runs in polynomial time and can output something with small test error. Yes?
Do we need to make any complexity theoretic assumptions?
Of course. Of course. Of course. Of course. I will go there in a minute. So the corollary is that overspecification alone is not enough for efficient learnability. And now to your comment. So basically all computational lower bound are based on some hardness assumptions. Here too, we are based on hardness assumption. So what we need to show here for the lower bound is a lower bound for improper learning. Improper learning is what I described before, where when the learner is not restricted in any way, the only requirement from the learner is to output a predictor with small test error. This is the only requirement. And it's quite difficult to come up with lower bounds showing that the learner cannot output any trick, cannot use any trick in order to solve the problem. So how do we show hardness of improper learning? So there are basically the classic thing in computational learning theory to show hardness involves cryptographic assumptions. But here we have a new method for deriving lower bounds for improper learning, which is not relying on cryptographic assumption, but relies on average case complexity assumptions. Things like you have a DNF formula, and you need to know if it is satisfiable or not satisfiable. Now, the formula can come either to be completely random or be satisfiable. And what the algorithm needs to do is to know if we are in case A or in case B. So such things are assumed to be hard, and using this assumption, we can show many nice things, including showing that learning DNFs is hard, which is an open problem about 30 years, and also that intersection of little omega of 1 half spaces is hard. Now, neural networks with little omega of 1 half spaces and sigmoidal or sine functions can implement intersection of half spaces. Therefore, this result tells us that no algorithm can learn neural networks of small size, even if we're in depth 2. Okay? And by the way, in these SNPs, using similar technique, we show computational statistical trade-off. So this technique is really nice for coming up with a new method for establishing lower bounds for learning algorithms. Anyway, back to neural networks. So things looks really, really bad. Okay, even very, very simple networks are difficult to learn. And what we need to do, yeah?
So the result you just stated is true no matter how much data you get from?
No matter how much. Of course, if you have exponential data, it can help you. But then the restriction on the algorithm is it to be polynomial. So having exponential data will not help you because you need exponential time to go over it.
So polynomial
polynomial in D, in the dimension. Okay? The only restriction on the algorithm is to be polynomial in the dimension, to run in polynomial time in the dimension. Okay? Okay, so we need to make more assumptions. As usual, when we have something hard, we try to make more assumptions. And the change that I suggest is to change the activation function to something simpler and to look at the square function as the activation function. So what we obtain is what people in neural networks call sum product networks, because basically what the network does is just summing numbers or taking multiplication of numbers. This is the only thing that we do. And I will show you that it is possible to efficiently learn some product networks of depth 2. Okay, so okay, this one I showed. Okay, so here is some depth 2 polynomial network. So we have the input layer, then we have the hidden layers which compute inner product with some vector and then take square, and then we have sum of this. This is the output layer. So looking at this, we want to learn the class of all functions that can be implemented in such network. And formally, we take the hypothesis class to be the function that maps X into sum of R elements. R is the number of hidden neurons, Wi, vi.x square, and we put restrictions, as usually in neural networks, on the two norms of the weights. We want the two norms of the vi's to be exactly 1, and for the output layer to be order of 1. Okay? So this is the type of networks that we would like to learn. This is still, learning this is still NP hard, even if the loss function is convex and nice, like square loss. But here, a slight overspecification with a greedy algorithm works. OK, so what we can do? Let's start with a very trivial thing. Suppose we take these square hidden neurons. Now, what we have here is a second-order polynomial, right? So we can express it by taking all the monomials of degree 2 and putting weights on them. Then we get a class that contains this class, because this class is a subset of second-order polynomials. Okay? So just taking all second-order polynomials will be larger than h. Okay? And then if we just put these square hidden neurons, we now can learn it trivially. Okay? Because in the first layer, we do nothing. We just take all the products. And in the second layer, we just learn a linear predictor. So this is trivial, but this is maybe too much. The question is, can we do better? Can we be order of R? Can we learn it with order of R hidden neurons? And the answer is, yes, we can, using forward greedy selection. So what is forward greedy selection? We probably heard about it today. It is closely related to the Frank-Wolfe algorithm. So we would like to minimize a convex function R of W, but we have a non-convex constraint that the L0 of W should be smaller than R. Now, for any subset of features that are allowed I denote by W sub I the vector whose support must be in I and minimizes the problem. Now, solving this problem is easy. It's a convex optimization problem. Okay? So finding Wi, once you know I, you know the support, finding Wi is just a non-constrained convex optimization problem, which can be solved using any method that you like. OK, so what forward greedy selection does, it starts with I containing no features. And then for t equals 1, 2, etc., we pick some coordinate j such that the gradient in the direction j is close to the maximal. So close in the meaning that the j's coordinate of the gradient is greater than 1 minus tau, the maximal coordinate of the gradient, where tau is any constant between 0 and 1. Okay? Then we take the new set J to be the union of what we have until now and the new element J. And then we have a replacement step in which you can choose I to be any set such that R of W sub I is smaller or equal to R of Wj. So of course, the trivial choice would be to take I to be exactly J, but if you do something better, it's just better. Okay? So this is the basic algorithm. What can we say about this basic algorithm? So we can say the following theorem assumes that R is beta smooth with respect to some norm, and I only require that the norm of any singleton will be 1. Okay? Then for every epsilon and every bar W, if we run forward greedy selection for 2 beta, the L1 square norm of W bar over 1 minus tau squared time epsilon iterations, then it outputs W such that the value of the objective at W is only epsilon away from the value at W bar. And the L0 norm, the number of non-zero elements of W are trivially K because of the definition of the forward greedy selection algorithm. So few remarks about this theorem. First, the dimension of W has no effect on the theorem, which is very interesting. And you can even work in infinite dimension space. And the greedy algorithm still needs exactly the same number of iterations. Second, W bar here is not necessarily the optimum of the original problems that we're trying to tackle. It can be any vector. Okay? This is also an important thing because maybe the optimal vector would not have small value of a L1 norm. But here you can say it suffices that you have a vector with both low L1 norm and good performance in terms of the objective R. Okay, and another observation is that if the L2 norm of W is O of 1, then you can easily see that the L1 norm square is order of the sparsity of W bar. Okay, so remember that in neural networks, we restrict the L2 norm of W bar. It translates to a nice relation between the square L1 norm to the L0 norm. Okay? And the bound also nicely depends on the approximation parameter tau of the finding the largest element of the gradient.
Remind us again of how tau is used in the algorithm?
Sure. Here is tau. So usually, in what Rob described in the morning, we want to find the coordinates and maximize the gradient. Here we only need to find something that gives a multiplicative approximation to this maximizer, which may be much, much easier.
Well, but also, but if you now, but your complexity results, one would think tau equals 0 should be better. But you've got
it is better. It is better.
Oh. Thank you.
Sure. Okay. So now let's apply the forward greedy selection algorithm for the problem of learning neural networks of depth 2. So what I'm going to do is I will think about the network. Let me go back to the network. So the network has 2 components. There is this W, and there is all these vectors V. So I will start with all possible vectors V in the hidden layer, but I will maintain W to be a sparse solution. So if W is a sparse solution, it means that effectively we can forget about all the weight vector in the middle except those that have non-zero W. Okay? So I will apply forward greedy selection on this layer, assuming that this layer contains the entire vectors V. Okay? So here, let S be the Euclidean sphere of RD. This contains all the vectors V that you may consider. And now think on W as a mapping from the sphere to R. So think about the coordinates of W as being indexed by every possible vector in the sphere. Now, each hypothesis in H corresponds to some W bar with L0 norm equals R and L2 norm equals O of 1. R of W bar will be the training loss of the hypothesis in H corresponding to W bar. Now we can apply for a greedy selection for order of R over epsilon iterations, and this will yield a network with R over epsilon hidden neurons, and the loss would be at most RW bar plus epsilon. It means that if we have R hidden neurons in the best hypothesis in our class, then we need R over epsilon hidden neurons to learn it efficiently to accuracy epsilon. Okay? Now, the main caveat is that at each iteration, we need to find V such that if we take the derivative of RW with respect to the direction V, V now is a vector, then it should be greater than 1 minus tau times the maximal coordinate with respect to some U. Okay? So how we do this? Luckily, if we take the derivative of RW with respect to V, we obtain this expression here. Now what we have V transpose times some matrix times V. This matrix is something that we know because it's expectation over the data set, taking the gradient of the loss at the current solution, which is sparse, so we know to calculate this, and Y is a label, time X transpose. Okay? So this is a matrix that we know to calculate efficiently. And now to maximize the gradient is to maximize this expression, but this is exactly an eigenvalue problem where we want to find the maximal eigenvalue of some matrix. Now, we can do it exactly, but we can do it in linear time if we set tau to be 1/2. Okay? Because if we set tau to be 1/2, we can apply the power method and solve this in linear time. So the resulting algorithm is described here. How much time do I have? 5 minutes. OK. So basically, here is how to do it efficiently. And the only change that, if you remember, in the forward greedy selection, I allowed a replacement step where you can set I to be any set of indices for which the objective is just smaller than the objective of just adding the single new element to it. Okay, so this can be also implemented efficiently in this particular case. Overall, the complexity depends linearly on the size of the data if we choose tau to be a constant. OK. Let me just one more word about what I just did. So those of you who are familiar with minimizing matrices subject to low-rank constraints, what we did is exactly this. Because actually, the predictor can be described as a matrix with a low-rank constraint. OK? Oh, sorry. Other direction. OK. So what we saw so far is that learning depth to sigmoidal network is very hard, even if we allow overspecification and even if the number of hidden neurons is very, very small. On the other hand, if we replace the activation function from sigmoidal to square activation function, we obtain some product networks, and learning depth to some product networks is tractable if we allow slight overspecification. So we needed R over epsilon instead of R hidden neurons in the intermediate level. Now, an immediate question, what about deeper networks? After all, we want to learn deep networks. So the short answer is that I don't know. What I do know is that if you want to learn very deep polynomial network, say of depth polynomial in D, even if their size is still polynomial in D, so the overall network is polynomial in D, just deep, okay? Then this is still hard. So very deep networks you cannot hope to learn. And the idea of the proof is that you can approximate sigmoid function with polynomials of degree poly D. So once you know to, had you knew to learn such networks, you could mimic sigmoidal networks, which we saw that this is hard to learn. Okay? So what else can we do? We can also impose some distributional assumption. And of course, it should be easier to learn under certain distribution assumption. The question is, what are reasonable distributional assumption? So one direction is to assume that the data lies on algebraic manifolds. And then there is a recent algorithm from last year, ICML, which is called Vanishing component analysis, which enables to find a crisp identification of such algebraic manifolds by finding the generating ideal of the data. And this can be done efficiently. But the theoretical guarantee is still not satisfactory because we are still working on to make it both computational and statistical efficient. OK, so let me just wrap up. I think I already summarized this. So let's go to the open problems. Is it possible to train some product networks of depth 3? Even this is not known. If the answer is yes, what about depth log D? We saw that poly D is impossible, but maybe log D is possible. Another open problem is to find a combination of network architecture and distributional assumptions that are useful in practice and lead to efficient algorithms. So I would like to thank my collaborators. First, Ohad Shamir, that was here before. We are working together on trying to find efficient learning algorithms for neural networks. The greedy algorithm for low-rank matrices is a joint work with my student Alon Gonen and Ohad Shamir, and it is based also on a previous paper with Tong Zhang and Nati Srebro. The lower bounds are with my student Amit Danieli and with Nati Lineal, and the VCA algorithm is by all these people. And let me just wrap up by a shameless advertisement to my new book. So thank you very much. They use sigmoid activation function?
Yeah, so that's all. So they have to solve an NP-hard problem at every step. But still, if I remember well, the setup is similar.
Mm-hmm. Actually, I don't know. I need to read it.
So just to be clear, your sum product networks has nothing to do with the sum product networks of Poon and Domingos?
It has the same architecture, but the training is very different. Because they also just use sum and product, and we also just use sum product. So in terms of hypothesis class, it's the same. In terms of how to train it, we show that two-layer networks can be trained efficiently. Can you please speak up?
So that's not exactly correct. So you're talking about arithmetic circuits. Some product networks have certain structural restrictions that is not present in your version. So it might be better to just call them arithmetic circuits.
OK. So I take it back.
Okay, one last question.
Yeah, it's a naive question. Do some product networks have some universal approximation?
Yes, that's a good question. So the answer is yes, because you can approximate any polynomial, any function with a polynomial, right? Any reasonable function, Lipschitz function. Okay, but again, I think that the property of universal approximator is not interesting because if you insist on of universal approximator, then first there are many other ways to obtain it. Second, you must use exponential size networks.
Okay, let's thank the speaker again.
Thank you.